Hi everyone, my name is Ahmad Haikal bin Abdul Azim.
My name is Muhammad Fatih bin Shuhaidi.
My name is Ahmad Lukman Fatih bin Mohammed.
My name is Zulharis Farhan bin Zulifran.
My name is Lim Wei Chen.
And today we'll be presenting to you on our thermodynamics concept, which is power generation by hydroelectric turbine.
Alright, right now we're gonna explain our project, which is hydroelectric generator. So our main goals is to prove the first law of thermodynamics, which is it states that the energy cannot be generated or destroyed. It only can be transformed or transferred from one form to another form. So this will be explained by Haikal.
Okay, so as you can see, when we pour water into this tank, which is our water reservoir, the height difference in the water tank produces a pressure. So this inlet velocity, the outlet velocity of the water, is calculated by square root of 2gh. So this velocity is the kinetic energy, and as the water goes down and touches the turbine, there's also a height difference producing additional kinetic energy. So once the water hits the turbine blades, it will produce a rotation on our hydroelectric turbine. And this rotation is at a certain RPM, at a certain angular velocity. And that angular velocity, and basically the kinetic energy is transferred into the rotation, producing work done. So it shows that the kinetic energy is transferred to mechanical energy, and that mechanical energy is transformed into electrical energy, which is proven by the change in our ammeter. So that is it from us. I will now proceed to the next part.
Alright, so this is some of the applications that our prototype is being used for. So the most common application is the hydroelectric power plants, which is dams. Water is stored at a height, flows through turbines, and spinning a generator. It is used for large-scale electricity supply, grid stability, and also flood control and irrigation. Examples of these are the Pelton, Francis, and the Kaplan turbines. Second is the run-of-river power system. They don't use large dams, but water from rivers directly turns the turbine. It is used in remote communities, mountain villages, and also small-scale renewable energy systems. Their benefits are low environmental impact and continuous operation if river flows steadily. And the third part is the micro hydro system, which is a small turbine, less than 100 kilowatts, for homes or small facilities. The applications is for rural electrification, farms or off-grid cabins, and also remote factories or telecom towers. So another one of the application is the pump storage hydroelectricity. It is used for electricity storage, energy storage. Water is pumped uphill during low demand and it is released to generate power during high demand. So this work like a battery. It is peak power supply, grid load balancing, and used for storage for renewable energy like wind or solar energy. So that's it from my part.
Alright, so we are the ones that make this model of prototype. So let me briefly explain what our prototype consists of. So first of all, here is the water reservoir, our water outlet. It will generate the water for heating the turbine. So right here we have the turbine. The turbine is connected to a DC motor. So when the water hits the turbine, it will spin. When the turbine spins, it is connected to the DC motor. So when it spins, it will become a generator. A generator, it will produce electrical energy for our system.
So according to the equation shown on the screen, our heat transfer would be 0 as there's no heat transfer in our process. Then our mass flow rate also remains the same, and so does our height difference, because as mentioned by Haikal, our velocity 1 is the velocity just before it hits the turbine, and V2 is the velocity right after it hits the turbine. So there's a change in velocity, and there's also work produced in the form of electricity. So as you can see, this is your V1, your V2, and energy is produced as the turbine spins.
Several assumptions were made throughout the calculation for our simplicity. First of all, we are assuming that there is no heat transfer throughout the whole process, therefore we can eliminate Q input, which is the heat transfer element of the equation. Second, we are also assuming that the mass flow rate is constant, therefore assuming steady state, there is mass in equals to mass out. Third is that our velocity input is the velocity just before the water hits the turbine, whereas the exit velocity is the velocity of the tangential speed of the turbine. And finally, we are also assuming that the enthalpy for the first state and the second state is the same. Why are we assuming this? Because we are assuming that the pressure between the first and second state is equal, which is equal to the atmospheric pressure, since the water is exposed to the atmosphere, and also that the temperature remains constant throughout the process.